like let us know what that we're getting going. So I think we should be getting started very soon. So hello to everyone who's joining us from around the world. We're delighted to have you back for this next webinar with YR, and we're looking forward to continue on the series all through 2021 as much as we can. So we're joined today by Dr. Gwynn Sturdevant, who's Sturdevant, sorry, pardon me, and she's joining us from the United States of America in DC. Just before I introduce you properly, I'm going to sort of say hello to all of the R user groups who are joining us today. We have Berlin R, Barcelona R, London R, and many more. So it's great to find out where the R community is based. So if you're watching us on YouTube, just drop a line and let us know where you're coming from, because we always love to see that, all the people around the world, and particularly our regulars there. We have some there from around Chicago, so sort of we're thinking of you as well. So yeah, I think actually, Gwynn, I'll just let you take over there. And just one more thing actually, just to sort of thank our sponsors, Jumping Rivers, who are supporting this series and who are good supporters of our user groups and have been for a long time, and we definitely appreciate their support. So Gwynn, I'll let you take over there. I'm going to go mute and stop the screen. And
okay, hi everyone, welcome. I'm so excited to be here, and it's just amazing to me. It's a whole international group of us getting together to talk about R. R's been around for so long. I just think it's amazing that it's grown so much in the past couple of years. I'm just like so excited and so impressed. My name is Dr. Gwynn Sturdevant. I'm a postdoc at the Laboratory for Innovation Science at Harvard Business School, and I'm here to talk about efficient computations in R. So oops, let me see. Let me just make sure I can click through my slides. So the agenda today, I'm going to briefly talk about my UseR 2020 talk. You can find the whole thing on my website if you want to know about it, or you want to watch it. And then we're going to talk about when you should vectorize functions, because the efficient computations that I'm talking about today mostly have to do with vectorizing functions in R, which is a way to make computations run much quicker. And then I'm going to do two examples of vectorization, and one is finding eigenvalues, and the other has to do with mismeasured survival analysis. So here we go. So here's a little bit about, this is my UseR 2020 talk from last year. I'm excited, can't wait for UseR 2021. And so what happened is that I was dealing, at the time that I wrote this talk, I was dealing with transportation statistics, and I was looking at arrival times for flights from Atlanta from the 100-mile circle. So planes come in from Atlanta, and they come in from a 100-mile circle, and then they go to the 40-mile circle, and then there's wheels on. And then there's ways to estimate from, there's called a terminal arrival efficiency rating that goes from the 100-mile circle, and when a plane crosses a 100-mile circle, how soon will it wheels on? So there's an estimate that the FAA uses, the Federal Aviation Administration uses to compute that. And I was looking at means. I was trying to find an estimate for the mean of this, and I was using data from Atlanta in, I think it was 2016. Don't quite remember the year. But anyway, so I was writing this, and one of the first things I did was write up this tidyverse function. And I take the data, I sample, I pull the splits, and then I find the column means, right? And so the tidy means was running really, really slow, and I really didn't want to take all the time to wait for the function to run. I really wanted to do the write-up. And so I quickly wrote a vectorized function, and here you can see that I take the sample, and then replicate is a function that's really good when you're doing when you're vectorizing functions. It takes an input, the number of times you want to do it, and it also takes a function, and then it does it over and over again. And then I take the call means of that function, and that was the vector means. And lo and behold, this ran much faster. And I couldn't believe how much faster it ran. I was really, really surprised because often we learn that the tidyverse is a wonderful way, but I was just so surprised to find out how slow it was. So I used a micro benchmark package to find out exactly how much slower it was, and you can see that this is 9 times as fast. It's much quicker to run it in vectorizing it than it is to run it in the tidyverse. So the other thing I wanted to talk about briefly on this slide is the composition of functions, or the order in which functions are done, in which I'm doing the computation. So in the tidyverse, it's much more like the English language. We do one thing, then we do another thing, then we do a third thing, and it's a much more this is how and this is of course how we read English. We read English straight down, but in math, the way that you compose functions is you go inside and you go out, right? So you start with something and then you go out and then you go, and I think I remember learning this in high school. You compose simple functions, with polynomials, and just to see, just for practice. So it's a different way of thinking about these things, and I just wanted to point that out here. So, right, now I've talked a little bit about my USAR talk and why it's important to vectorize, or how much vectorization can give you, or what an advantage it can give you. I'm going to talk a little bit about when to vectorize. So here's this plot here, and I'll just tell you I really like vectorizing functions. I kind of do it all the time. My tidyverse is not that strong. It's still something I'm really want to work at and get better at one day, because I think there's value in it. But let's just look briefly at this graph. So if it takes 30 seconds and you do it 5 times a day, across 5 years, it will take you 3 days, right? So the idea is how long do you want to spend? So just be wary. How long do you want to spend trying to get this code to run quicker if it doesn't take very much time to begin with? The other thing I want to talk about is that if you're doing a model development, for example, if you're writing a package in R, it might be a good idea. You want it to kind of run quickly. If it's some kind of model that you're developing, and it's a new and a different one. And if, for example, if you're giving a talk to a client and you want the results to pop up really quickly, you don't want to spend a lot of time with your computer chugging away. If speed is really important and you're giving a presentation and you want to run something in real time, it might be important to think about vectorizing that coda. And then also if you have, so there's kind of small data, like perhaps the iris set, which is, the data set that we deal with in R, that's very common, or MT cars. But then you have really, really big data. So if you're doing really, really big data, it'd probably be better to work with MongoDB or SQLite and do some kind of work with a database. But then there's this kind of nebulous kind of middle ground where you have a bit of coding, and you want to get your results a little bit quicker. So that's when you think about when to vectorize and how to do it. So now I'm going to talk a little bit about eigenvalues and how to to vectorize the function in eigenvalues. To vectorize eigenvalues to find a little bit of coding that will help you find eigenvalues if you have a 2x2 matrix. And I originally started this wanting to do singular value decomposition, but it ended up being that R doesn't deal well with non-singular, base R doesn't deal well with non-singular matrices. So I ended up just finding the eigenvalues and not going any further than that. Also, there's an SVD function, singular value decomposition, that is really good at that solves these problems really easily. And so I, not only was it a little bit more difficult than I wanted to do it to be, but it was also futile. So I decided that I would just kind of keep it simple, 2x2, and just try to find the eigenvalues. So here we go. Here we have this 2x2 matrix, and one of the reasons that singular value decomposition works so well is that it's A transpose A, and so whatever matrix you have ends up being a square matrix, which means that you can find eigenvectors and do, it's much more flexible and find identities and so on and so forth, and inverses. So here I have A is A, B, C, D, and then A transpose is this matrix here. And what I'm going to do is, simplify it. The first step for me when I vectorize something is I try to do as much of the algebra as I can. I write down or do a piece of paper. I do work through the algebra to figure out exactly what I want the code to do. Okay. So here I have A transpose A's, and I've found A transpose A, and then I've subtracted off the 2x2 identity matrix times minus lambda, right? So if you look at A transpose A's, you can do the algebra. You'll end up with A squared plus C squared, AB plus CD here, and the rest of the matrix. I just worked it out by hand, and so the determinant of this needs to be 0, and that's how we work through it. So now I've kind of simplified this, right? So what I'm going to do is I have this determinant, and I need to find the determinant of this matrix here. So it's going to be this minus, it's this times this minus this times this, and that has to be 0. So I have this times this minus this times this, and now what I'm going to use is quadratic formula. I'm going to use this. This is a quadratic equation, so I'm going to use a quadratic formula. You can see that the coefficient for the lambda squared is 1, which is nice because the quadratic formula means A doesn't need to be included in the formula. And then the coefficient for lambda is, A squared plus B squared plus C squared plus D squared, all negated. And then this is my constant coefficient, okay? And so now that I found that, I'm going to write some functions, right? So I don't know if in the US we have Halloween, and we had, a very different Halloween this year. It's October 31st for us, and usually all the kids come around, and they have these little kind of pumpkin buckets, and you give them to the kids. You give candy to the kids, but because everything had to be no contact, there in our neighborhood there were several of these candy chutes, so that the kids could receive their candy without with remaining socially distanced. And those chutes are very much like a function for me in my view. So let's look at some functions that I wrote here. So this is to find the coefficients, and the coefficient for lambda was the sum of, was this. So all I did was change the matrix to a vector and square it and sum it. And then the constant coefficient is the first column squared times, squared summed times the second column squared and summed minus, oh, this should be in minus. I'm sorry, I didn't get that right. Minus the product of this and the product of the first row and the product of the second row all summed together. So it's just a nice way to find this. And then I output the negative because it was the coefficient was negative from before, and the constant coefficient. So that's one function. The other function that I need is the quadratic formula. Of course, we saw before that A was 1. And so what I have is I'll find that the discriminant, B squared minus 4C, and then I'll have the plus and minus of this function here, and then I'll output that. So the other thing I want to point out here is that we have to do this from inside out, right? So we're doing this from inside out. And so when I compute this, I need to find the coefficients, and then I put the coefficients in to this eigenvalue, and find the eigenvalues function there. All right, so if I have this matrix, I can input this and find the coefficients. So, right, that's all I have to really say about that. Now I'm going to spend the rest of the talk largely on this mismeasured survival analysis stuff that is, I think much more interesting and a little bit more challenging. Okay, so here we go. Oops. So I don't know if you remember this tweet from Elon Musk. This was on November 13th. He took 4 COVID-19s. He took the rapid COVID-19 tests. He took 4 of them on the same day. 2 were positive and 2 were negative, right? So they were different values, and he was like, "What's going on? How come I have 2 positive tests and 2 negative tests? What happened? Do I really have COVID or not?" So I think. As someone who knows a little bit more about data and knows a little bit more about testing, I can tell you that the rapid antigen test traded speed for accuracy, right? So you get your results very quickly, but they're much less accurate, right? And that's why the rapid antigen test isn't the gold standard. You actually have to sit and wait for the test. You have to take a different kind of test if you want to take a gold standard. But there are other situations where you end up with a noisy test that makes it really difficult to determine whether or not something has occurred. Now, for one example of that is hypertension. So your blood pressure goes up or down depending on the time of year, depending on if you're sitting and standing, depending on if someone in a white coat is in a room. And then there's also traditional measurement error, which is that different doctors will give people different values of blood pressure, even if it's a recording. They've done a test where they recorded someone, the heartbeats and all this stuff, and different doctors gave it different values. So there's this, it's very difficult to figure out when someone actually has hypertension, which is blood pressure above the threshold of 130/80. So the other times, the other measurements that are difficult to diseases, or I'll say, or issues that are difficult to diagnose, difficult to diagnose is high cholesterol, because your cholesterol value changes depending on what you've eaten, and the other one is cholesterol and fasting blood glucose, which is used to determine if someone has diabetes. Right, so these are noisy measurements. It's very difficult to determine if someone actually has the disease. In terms of high blood pressure, actually the best way to do it is you have someone wear an ankle bracelet for a week, and then you can figure out what the actual value is. So their blood pressure is without the noise. So it can be a really challenging thing to do. But let's just go back to COVID, and we'll talk about, for example, you want to find time to event. So let's just say, for example, that the only thing that you have is this rapid antigen test, and you're trying to find the time to event of someone, a time to intubation, perhaps, of someone who is on a treatment and someone who's not on a treatment, right? But we only have this kind of noisy measurement that does not give us an accurate picture of when things are actually occurring. So what we do is we model for this, and we model for it using this is the likelihood for discrete survival analysis mostly, and then we have this TI observed. So in this section there are 2 variables. There are 2 time values. One is TI observed, which is the time that we observe, and then the other is TI, which is the actual time, and that is unobserved, right? Because we have a noisy measurement, so we're not actually certain when things occur. And we also have the same with DI. So we have DI observed, and then we actually have DI. Now, some of you may have noticed that we have this capital gamma I and delta IK. So those are used to account for the mismeasurement. So here's this. We have the gamma I, and this is what we're assuming, and this is a measure of specificity. And so what we have here is time varying specificity. So we have time goes from 1 to ti minus 1. J goes from 1 to ti minus 1. And so each time point has a different value of a different accuracy level. So we're accounting for a different accuracy level at each time point. And then here we have, this is also specificity, and then 1 minus, so this is, this would be for a true negative, and then this is a false negative and a true positive. So we have these values here that we're thinking about, and we have to include them in our full likelihood, because we're accounting for mismeasurement. Okay, so here we go. That is really icky. It's really, really horrible. And this is why I always talk about simplicity being one of the first things that you do. You really want to make sense of what's going on and have a good idea of what the function is and write it down and do the algebra before you even start trying to vectorize or do any kind of coding, right? So let's go through here. I'm just going to explain it a little bit. And of course, we're going to vectorize. Excuse me, I probably didn't mention this. The vectorize a derivative with respect to gamma naught L. So that's one of these gamma naught L's here. Okay, so if we look at this, what I want you to notice is that we have this and this, as well as this, right? And what are they? They're the same thing, right? So I'm going to use a substitution because this is really difficult to look at. It's difficult to think about, and it will make it easier, right? So I have this HR, which is, I don't want to go through, 1 plus e to the gamma naught j. It's a hazard risk function, all to the negative e to the xi transpose beta, right? So we have that, and then we also have the complement of the hazard risk function, which is this here. So we have both of these. So this is allow us to simplify this formula quite a bit. So I have here, and I can just put this here, and put this here, and this here, and then I think it's for me, it's much easier to look at. Okay, so now we've simplified it to the most that we can. What we're going to do next is look at clarify and figure out exactly what's going on here. So let's look at an example. And for this example, I'm going to let ti observed, to be 5. So what I have here is j goes from 1 to 5. And so this gamma naught j is just going to be, it's going to be the hazard risk function evaluated at gamma naught 1 times the hazard risk function evaluated at gamma naught 2, all the way up to gamma naught 5. So that's the first part of this function. I'm just going to move this down. Here we go. So it's the first part of this function, is all of these are evaluated at gamma naught 1, gamma naught 2, and then gamma naught 5. And what we have here is this k is 1 to 5 of j equals 1 to k minus 1, and so on and so forth, right? So let's just let k equal 1. And you can see here, then we would have j equals 1 to 1 minus 1. So this whole thing will go away. So if k equals 1, this whole thing will go away, and all we'll have is the complement of the hazard risk function evaluated at gamma naught 1 times delta I 1. Oops. And that's that, right? So if we allow k to be 2, we'll have the hazard risk function evaluated, so this will be 1 to 1, right? Evaluated at gamma naught 1, beta times the hazard risk function, the complement of the hazard risk function evaluated at gamma naught 2 times delta I 2. So here we go, and there we go. Right, so I think you can see what's happening, right? If we go up to 3, you can see that I'm going to have 2 of these that will be multiplied together times the complement at the end and the delta I3. So this is the way that we build it up. So we have to have a good idea of what is going on in any kind of coding before we can begin to vectorize it. And then, I didn't add the fourth one, but you can see that this is the pattern. This is the pattern, and this is what we're trying to produce. Okay. So before I go on to this, I want to take some time to talk about this capital gamma 1 and talk about a different way of indexing. Oh, sorry, I forgot about this. We're actually not vectorizing this. My mistake. We're vectorizing the derivative with respect to gamma naught L. And so what I'm going to do, this isn't a derivative taking class, so we're not going to go through the whole derivation in much detail. But if you can imagine that I'm taking the derivative of this function with respect to gamma naught 2, all of this will be kept constant. And then I'll have to take the derivative of the hazard risk function evaluated at gamma naught 2 with respect to, the derivative with respect to gamma naught 2 of that function. So, which is what I have here. I just take this. So I multiply all of these out, and then I add on this. And I'm not going to go through the rest of the derivation. Okay, so now I'm going to get to indexing, and I'm going to talk about a different way to actually index. So there is, I think some people know that for loops aren't, you try to avoid for loops, but I want to discuss other things that you can do that will, that make your coding run faster, that do not entail using for loops. So, I'm going to use that by talking about the capital gamma I, which I pointed out is right here. So we have this gamma I. And so in this case, we have some true negatives and then a false positive. And so we're multiplying the probability that this might occur, right? And so what I want to do is I want to talk about, we have J goes from 1 to Ti observed minus 1. And how can I multiply this out, right? So how can I find a way to find this product that doesn't involve for loops? So if I have phi go from 0.08 to 1, and I've just made some Ti observed here and some Di observed. Now these, I'm just going to point out, are this means that no event occurs. So we are talking about intubation with COVID-19 with some kind of medication. And in this case, it means that no one was intubated. I don't know. This doesn't involve X, so we don't know if they were in treatment or control group, but in this case, they aren't intubated. So here we have phi goes from J equals 1 to Ti minus 1. And what I'm going to do here is what this means is that in this case here, if I have this data, I'm going to have, I'm just going to multiply this product here is what I want to focus on. And that product is just going to be this, right? It's going to be 0.8. Because J will go from 1 to 1, and so all I'll be left with is this. Now, I'll point out here that Di observed is either 0 or 1, so one of these two will go away. It's a binary outcome. Either you're intubated or you're not. And so one of these will go away, and in this case, this one will go away. In all of these cases, this one will go away, so we will be left with this. So we're going to multiply this whole thing. The whole thing is going to be this number times this number. Okay. So let's look at 5. And in the case of 5, we're going to multiply these top 4, these first 4, and then the last one we'll multiply it by 1. In this case here, we're not going to have any, right? We're going to just have, we're not going to have any here. We're just going to multiply. We're just going to have this one right here. Okay. So that's kind of the way that we're building this up. And that's what we need to think about. Right. And so for each of these, people that are in our trial, we need a line of phi, right? So I have this lots of phi here, and I make this lots of phi. I just have it be, repeat, I make a matrix of it. I repeat phi many times, and I have one for each person. And then what I want to think about is which of these need to be 1, because 1 is the additive identity, which means that I can multiply. If I can multiply across all the columns, then I can do that really quickly, because R is a vectorized language, which means that things run very fast in that way, and when I'm not using for loops. So here I have lots of phi. And let's just go through this one again. I have the 2, so I just need this one, which means that all of these need to be 1, right? And then I have 5, which means that these 2, which happen to be 1 in this case, but don't necessarily have to be 1, need to be 1. And then if I have 1, then it's all of them need to be 1, right? So what I'm doing is I'm going to index off of this lots of I to get these lots of phis, right? So here I have all these are 1. Here I have the whole thing as 1. And now if I can come up with this matrix, if I can come up with this matrix, then I can just do I can just find the product, and I'll have made this, and then this can be very easily done. So let's look. How did I do that? So what I do is I index lots of off of lots of I. So what I do is I take lots of phi, and I say the lots of I that are greater than ti observed, replace them and make them 1. So that's the important part here. This is the important part. Replace them and make them 1. And then this part here involves, I have phi, the last of ti observed, right? Because whatever ti observed, it's just going to pluck that off, and then I'll have 1 minus di observed, right? So that these 2 statements here do this part, right? So you may look at this and think, oh my goodness, it's so messy. How am I going to do it? But you can see that in R, and this is one of the things I really love about vectorizing coding, is that it's just, 4 computations, right? So it's not a complicated thing to find. And I think it's really, really beautiful and really lovely to see it this way. Okay, so we're going to do another one like this. We're going to talk about the gamma IT. So I'll just take a big breath. Lots of math going on today, and I know it's not easy to listen to everything, but let's just take a big breath and relax a little. And okay, so here we go. So here we have this this phi, which I think everyone can understand how to do that based upon the last example that I gave. So it's just replacing. But what happens here when it goes between ti, this is the actual value of ti, and ti observed, okay? So let's think carefully about this. Oops, excuse me. And I have set a C, and I've come up with phi, and then I've come up with theta, and I have TO, or TI observed, and then I have the actual values of TI. And so I'm looking at them both, and I'm trying to figure out which of these thetas do I need to multiply? How do I come up with, when I have this theta, how do I come up with this product? That's what I'm trying to think about, okay? So the first thing that we notice is that it's not actually theta that we're multiplying, it's 1 minus theta. So we need to subtract 1 from this theta. So if I'm thinking about it and I'm building this in my head, I need to think about a matrix. Okay, the matrix needs to be 1 minus theta, it doesn't need to be theta. And then it needs to be, and then I need the TIs, it has to be between TI to TI observed, okay? So let's look here. So we have this person, the actual of the time that they were diagnosed, TI, and the observed time are the same, and they were not intubated, okay? So then I have, the actual time, so then in that case, let me just check. Yeah, this would go from TI would be 3, to TI observed would be 2, and so we won't have anything here. So I just need all of this 1 minus theta to be 1, right? So then let's look at the next one. So this person is diagnosed at 3. I'm sorry, their actual time, they were intubated. The actual time that they, the actual time is 3, and then the observed time is 5, right? And so we're going to be using, so this was going to be from 3 to 4. So it's going to be from 3 to 4. So I'm going to want to multiply. I'll have these two here that I'll multiply, and then 3 to 4 I'll multiply, and then the fifth one will be, yes, the fifth one will be, let me see. So this is 1, so that means that I'm going to multiply by theta, so it's going to be 1 here. Okay, so that's the idea. We want to think about what's going on. Let's just do one more. So here's, this is, the TI is 3, and then this is the actual time is 3, and the observed time is 5, and they were not intubated in our example. Oh, I think I just did that one. So that one would be the similar one to what I just did. The only difference will be this. So this one will need to multiply 3 and 4 here, except for it's going to be 0.05, right? And 0.025 instead of those actual values. It's going to be 1 minus that, which, so what we need to do is we need to think about if it's less than TI or greater than or equal to TI observed, then we want it to be 1, and that's how we'll find these middle products. So let's look, right? So I'm doing this here. I have lots of 1 minus thetas, and I talked about this one before. We want the whole thing to be 1. So if it's less than 3 or less than or equal to 3, then we want it all to be 1. This one, we're just going to be doing 3 and 4. So if it's less than 3 or greater than and equal to, let me see, 5, I think it's 4, then oh, it's just this one, right? If it's greater than or equal to 5, then it needs to be 1. And so we end up with a matrix like this, right? So we have all of these ones need to be 1, and then this one also needs to be 1, okay? So how do we get coding like that? And I've just given you it here. We have lots of, we do 2 indexes, right? We index it twice. And then I have lots of I is less than or equal to, is less than TI. And then all the ones that are greater than or equal to TI observed become 1. And that's the solution. That's what it is. Okay, so let's get back to our horrible, ugly thing. But before we do that, I'm just going to talk a little bit about dimensions. So when you're doing a lot of, when you're vectorizing coding in R, you often deal with a lot of matrices. And so you really want to be aware of the dimensions of the matrix that you're dealing with. And I will often just play with those, play with the matrices just a little to, and see, well, how big is the matrix? Is it this? Do I want to multiply the rows? Do I want to multiply the columns? So that I'm multiplying the right thing out. The other thing that I want to introduce you to is this function, is the outer function. The outer function takes 2 vectors and a function. It takes 2 vectors and a function, and it gives you every single combination of that vector, of those 2 vectors using that function. So here we have y and x, and we're taking, to the power function. So we have 2 to the power 1, 2 to the power 2, 2 to the power 9, and it goes through. So it's a commonly used function, as is replicate, which is something that I introduced you to earlier in when I did the bootstrapping for to estimate the population mean and the arrival times. Okay. So now I'm gonna go back to a slide you've seen earlier, which is that we go from inside to out. So let's go back to our horrible messy function. And I'm just going to talk about this part first. And gosh, I don't have very much time. I only have about a couple of 5 minutes, but we'll go through it. And the first thing I want to see is we're just going to start here, and we're going to work from the inside out, and what's in the inside, this hazard risk function, right? And also, I'll come with the derivative as in the next section too. So we have this hazard risk function, and so what I do is I use the outer function to find that, and I also have this derivative that I need to use. And here is, I set the seed. I have some gamma that I've made, which is this, and then I also have a beta, which is used here in this one. And I find some random x's. So this one's in usually, this one's usually 0 means it's in the control group, and 1 means it's in the treatment group. And so we have this, and then I find x beta, and I find the risk, which is this here. And then I take the hazard, I find the hazard there, and then I do, and that's given here. I just rounded it to 2 decimal places so that it would be easier fitting on the slide. And then I take my outer, and I have all of these. So this is, these are people, and these are time points, right? So I have person 1 at time point 1, at time point 2, right? And now what do I need to do? Now I need to, so that's right. So what I need to do here is I have this, and I make this B, which is this outer to risk function here, and I multiply. So I just multiply. Here's the derivative, and then I multiply across. I take off the whichever gamma it is that I want to do. Let me just show. I multiply the, it should not be a gamma L, whatever it is. It shouldn't be there. And then I multiply it by the derivative, and that is, this whole mess, which is just so ugly to look at. And one of my favorite things to say when I code in R is, look, it's 3 lines of coding. so we do this very complicated thing, and it actually is, much simpler than you might think it is. Okay, so the next one we have is the ugly one at the end, and I think we can go through it quick. So this is functions. This is another functions that we were talking about, and the function that I'm going to use here is call come product, and that is what it does is it takes the cumulative product here, right? And so what I'll be left with, and you see that I have used a for loop here, but the for loop goes not through the I values, which could take a really long time, but it goes through the columns, right? So if you're going to use a for loop, it's better to do it in the smallest dimension that's possible, right? So if you have 5,000 rows and 10 columns, you want to do it through the 10 columns. You don't want to do it through the 5,000 rows. Okay, so this call come prod gives and I'm not going to go back to my, maybe I will, but remember that this thing is just multiplied across many different times, right? So remember you have to find the product, and then you multiply this by the derivative with respect to gamma naught L of the hazard risk function, and the complement. Right. So this is, so this is an important function to write, and it's a simple function, and it shows, I think, a deep understanding of what is actually going on in this formula. And so, I can't say how important it is to actually have a good idea of what the formula says in order to write good coding that does what you want it to. So here is this. I've done all of this you've seen before, right? Except for that I've replicated B. I have B, and then I have B1, and then I find the derivative, right? And then here I take 1 and call cum prod b, which is just multiplying it all the way across. I take off the which gamma, right? Because I don't want that here. And then I take off the last one, which is the length gamma, which is this one here. And then I multiply it by the derivative, which is this. And I multiply it by 1 minus b here. Oh, right. No, this length gamma comes off because of the k minus 1. My mistake. The length gamma comes off because of the k minus 1. Oh, sorry, that's my last. Oh, here we go. Okay, so then I have lots of I, and I use A. So this is A is my matrix here. It sounds like I could get rid of this B1 here. So you know, anyway, I don't see that I use it anywhere. So it's important to, you know, clean up your code when you can. So then I use this one here, and I say lots of I. So the ones that the part of A that we're interested in. So that's this whole thing, and the ones that are between which gamma plus 1 and lots of ti become 0, and then I take the row sums. So this is kind of a little bit more complicated, but yeah. Okay, so the take-home message is, oh, you know, there we go. We've talked about it all. The take-home message is to avoid for loops and to try your hardest to do calculations in big chunks, because it's really important to, if you can do it in a big chunk, to do it in a big chunk. There's also a blog post that Noam Ross wrote on this, and there's some information about what's it called? Vectorizing coding in the R Inferno as well. So there's stuff there if you want to. Actually, Hadley has something in I think it's advanced. He has the advanced R book, and there's more information about it there too if you want to do some reading about it. But it's just a nice way to do it. So thank you so much for having me. And I'm not sure if anyone has any questions.
Hi there. Yeah, we'll have a few now. There's I'll just actually start off with one of my own, actually. It's not so much a...
Should I stop sharing my screen? Or
no, it's fine. Leave it up there. It's okay, yeah.
Okay.
What might happen is that somebody might ask a question that asks you to go back, so it just sort of save you the time.
Okay.
Just a sort of question to start off with. It's sort of more of an interesting talking point about the role of linear algebra in statistics, and people coming to statistics and data science just to sort of highlight the role of linear algebra and matrix calculations and so on.
Yeah.
Do you have any comments on that?
Oh, so it's very important. I mean, I want to it's so important. There was a Twitter thread that Daniela Witten wrote. And Daniela Witten is I don't know if you know, she's the head of department of biostatistics at the University of Washington, and she wrote a whole thread about singular value decomposition and how important it is. I remember you know, in algebra, linear algebra, a lot of times we think about each person is, you know, kind of a row, and then each variable is a column, and then there's all these manipulations you do, you know, X transpose, X inverse times beta, and so the beta is the estimates that you're looking for, and all of these the way that you find it is by doing all these matrix multiplications. But yeah, if you look on my Twitter, you'll see that I which is NZ Gwynn right here. You'll look up, I retweeted her singular value decomposition thread. I think she tweeted it under the Women in Statistics and Data Science Twitter handle, but there's, you know, I mean, it's dealt with. They use it to deal with missing values. You use it to address what are the other things? To address a lot of image recognition uses it as well. And the reason that, in particular, singular value decomposition is so nice is because you can do it on any matrix. You can give people whatever matrix you want, and they can always do singular value composition because it's always going to be a square matrix because it's A transpose A, right? So A transpose A, if you have an M by N matrix, then the transpose is going to be N by M, and so you're going to end up with an N by N matrix when you transpose it. And one of the things in preparing for this talk, I talked there's three things that it comes to. I don't actually have my notes here, but it's the matrices that they come up with are, I think they're what does it call it? I don't remember. I wish I could remember all the words, but I don't. Anyway, I think that's all I have to say.
Yeah.
I'm looking at my notes just to see if I can remember anything.
Yeah, I know. Yeah, I think that sort of covers it. It's a sort of call to arms to all career young data scientists to.
Oh yeah,
but it's linear algebra and matrices.
You must know linear algebra. It's so important, and I just think. Having said that, I don't really know the last time I used it.
Okay.
This talk, cognizantly, but I know that I used it when I was doing maximum likelihood estimation. It was really important, but just having an idea of what is going on. So anyway, I hope that helps someone.
Yeah, there's a very good conversation in the thread in the chat, in the quick Q&A. So just from the starting point is actually from the point of view of a beginner. You probably really covered this already, but just to talk a little bit about an elevator pitch about what vectorization is for somebody who's career young or new to this.
I would say that it's about avoiding for loops when you can, and if you're doing for loops through the through the smallest dimension of the data that you can. And then also using some functions like writing functions, which, and they don't, these functions are not, package ready, right? Because I haven't checked any of the inputs. But it's about making sure that you can know how to write, or can write a function, and then using that function to think about what needs to be done. And a lot of the work that I did, I have to be honest, in preparing for this talk, was that I did a lot of algebra, right? And I think that doing as many of the computations, if you want the coding to run quickly, do computations by hand and simplify it as much as you can by hand. And then, and I don't have my notes here. I was going to show you all I did pages and pages of computations just to have. I think I actually threw them out once I did it, but just to have a good idea of what actually the coding needs to be done, what actually needs to be done in the coding, and thinking deeply about it. I did talk to Ross Ihaka about this, and it is hard to vectorize coding. And one of the things he likes to say is that it's like being lit on fire and doing backhand strings through a hoop. So it is complicated, and okay. I'm sorry.
So a question there from TP Flow Specialist. Have you benchmarked or against C++ and NumPy? And I'm going to throw in Julia as well and MATLAB for vectorization of mathematical formulas.
So the one thing that I do know is that on average, vectorized coding, so I haven't done, so there is a package called RC++, which lets you do for loops in C++ inside R. And actually, and I saw something, I don't remember where it was, but it was talking about using the tidyverse, using for loops, vectorized coding, and then using RC++, and vectorizing coding even ran faster in R using RC++. And I'm not sure if that was something to do with R or if it is RC++, but I haven't compared it with Python or with Julia. Sorry, I'm not one of those. I don't use them. I don't use those languages too much.
Oh,
so
okay,
my apologies.
A question from Pete. If we want to apply these functions to more than one matrix, one or more matrices, the best way is to iterate using dot map or apply, or we can further vectorize the iteration.
So he's talking about them using map or apply.
Yeah. So using sorry, I just can't read the question. Using dot map.
Oh, I see. No, usually, I even had a discussion. I'll just be honest. I had a discussion with Charlotte Wickham about this, and because I didn't trust myself when I came up with this result, and I was like, oh my goodness, tidyverse is so slow. I didn't trust myself that in fact I was actually right. And so I spoke to Charlotte Wickham about it at the RStudio conference last year. So I came up with this, and I said, Charlotte, it's so weird. The tidyverse works so slowly. And so I really recommend, if you want fast coding, base R is much easier to use. The way that I understand it is that tidyverse has all these kind of layers built into it to make it much more usable and much more readable. Like I said over here, it's much easier for someone who doesn't have a long math background, but who reads English, to see the progression of the coding rather than this. And so tidyverse, I think, has done a lot in terms of readability. It's really popularized our made R much more popular, but at the same time, it is it has downsides. And I have to be honest though, this one is they just updated tidyverse like 2 months ago, I think, and they are trying to make it run faster. So that's great. But in addition to that, I have to just add something. We know that computers are getting faster as as they grow, and so but nevertheless, if you want to speed up your coding, the best thing to do is to try and vectorize it in base R.
Good stuff. Thanks for that. Oh, okay. So I'm just going to change the direction of the questions a bit, and a little bit about yourself. So you mentioned Ross Ihaka there in New Zealand. So that sort of begets a question. Tell us about your own background and your own journey in statistics.
Well, my own background. I think so. I grew up actually right outside of DC. And then I eventually, in my master's degree, went and studied abroad with a supervisor of mine for a semester at the University of Auckland. And so University of Auckland, and I was in the statistics department there. And University of Auckland is the birthplace of R. And so I think that was, let me see, it might have been like 2002. It was like, their semesters are different. Right now they're in their summer break. And so their semesters start in March. And I think I would have gone, 18 years ago, 19 years ago, I went to New Zealand for the first time. And so I was there, and then I ended up wanting to move back to New Zealand, and I ended up teaching high school there for a number of years. And then I decided I was going to get my PhD. And so I went to the University of Auckland, and I studied, my first R class was with Ross Ihaka. It was advanced statistical computing. I had to build a package in my first R class. And I was using base R, and I was so lucky because I had, there were 3 R core members at the University of Auckland, which are Ross Ihaka, who actually invented it with Robert Gentleman. Robert Gentleman is now at Harvard, and Ross Ihaka has retired from the University of Auckland. And then Paul Murrell, who is the graphics person, who has done a lot of graphics, and then Thomas Lumley, who was my PhD supervisor. I was very lucky because I got to work with them a lot, and I got to know them pretty well. It's one of those things where I was very lucky that I had people. Just so lucky that I had people who were so wonderful to ask millions of questions to, and
That's great. Yeah. So you're right at the crucible of the R world, the birthplace. Yeah.
I don't know. I mean, I think so. Some people would probably end, studying art with people like that and think they're really, really good at it. And I'm one of those people who studied art with people like that and thought, gosh, there's so much more I have to learn. So it really depends on who you are, I think, how you deal with things. But my own sense of my abilities is when you work with people who've studied it for have known it for 20 years or 30 years and actually wrote it, it's just you have a different perspective on it.
Yeah,
I think.
Tell me, you mentioned you're in DC, in the Washington DC, and everyone around the world knows that has been in the news a lot over the last month. So just actually the general question is, without asking too much, how you been getting on over the last few months as a data scientist, and how you been coping?
Well, I mean, as a data scientist,
just in your career and all that, just like how COVID and everything else, how's it going for you?
I think I'm really lucky. I have a wonderful position at the Laboratory for Innovation Science at Harvard. It has been a real challenge, especially January 6th when there was an attempted coup in the US. I shouldn't smile when I say that. I was lucky because we had ice cream and cake in the house, and so we ate some of that. I definitely thought a lot of, I don't know if you know Paloma, or no, yeah, I'm not sure, I can't remember her name, but she runs Our Lady's Rotterdam, and I thought of her. She's from Bolivia, and there were I think it went on for 3 months, the coups in Bolivia, in La Paz, where she was. And so I think it's something that and I didn't ever think would happen here. But I have to admit, I have to be absolutely honest, and this is just for me, when the 2016 election results came out, I just wanted to head back to New Zealand almost immediately. But my partner didn't. He's not from the U.S. He's from Ethiopia, and he didn't have citizenship yet, and he really felt like he needed to stay here, and he worked really hard to get citizenship in the U.S., and he wanted to stay, so he did.
Yeah, that's a very tough time. Just to say, we're thinking of everyone over there who's going through a tough time with everything going on in the world.
We have ice cream, and honestly, I feel like we have done this to so many other countries. It's our turn.
I can't comment now, but yeah, I think that's all of the questions really, and we've really covered a lot there. So it's definitely sort of some interesting material. Very much like a very new perspective for a lot of people on what R can do. I think that's very refreshing.
Yeah, well, this is what R was originally designed for, right? It was originally designed as to do whatever you wanted it to, and to do it quickly. And so and the flexibility of it is one of the attractions that I think made it take off. And tidyverse is a really important part of R, and it has helped R grow immensely. But for me, first of all, I decided I wasn't going to learn it because you couldn't write functions in it. But then they started writing functions, and now I do use it for some things. So especially if you want coding that's going to be easier for other people to read.
Yeah,
So.
that's great. Okay, I think we'll leave the Q&A there. Thanks very much, Gwynn, from joining us for
Thank
joining us.
you, and
And
thank
to
you for
everyone
organizing,
else,
Kevin.
we're going to just to sign off. So just before we go, again, I'd like to thank everyone from around the world who's joining us, and it's great. We really enjoy seeing how wide the R community is, and we love reading all the countries in the YouTube channel. We actually really get a real kick out of that. Also, just to thank our sponsors, Jumping Rivers, again, who are supporting us. We're back again next Thursday. I can't remember the name of the talk. I'm very bad. I'm sorry. But we're getting back again next Thursday. And also, just to start, also next Thursday, we have London, or sorry, next Tuesday, we're going to be joining London R. They have an event on next Tuesday. And, if you can join for that, please do. It's on the London R meetup page if you want to join that. So that's it. I think we'll leave it there. Thanks very much. And thanks to Lais Carvalho, who's also producing today as well. So she's the producer today. And so I think we'll leave it there. Okay, thanks very much. Bye-bye.